The focus of this lesson is on finding all the real zeros of a polynomial function. So we have a polynomial function here, f of x, and this process is pretty lengthy, but I have it broken down into 4 steps. And the first step is our starting point. So in order to find all the zeros, we have to have some zeros to start with. So our step 1 is to determine our possible rational zeros. And we do this by using the rational zeros theorem, which basically says that if you know the factors of your constant and you know your factors of your leading coefficient, and you take those and divide them by each other, then that'll give you your possible rational zeros. So I'm going to go ahead and list our factors for our constant first. So we will call these our p's. So it's going to be both positive and negative factors. And then, so our constant is the value 8. So think of all the whole numbers that evenly divide into 8. And you would come up with 1, 2, 4, and 8. So the positive and negative version of those are our p-values. And then we would do the same thing for our leading coefficient, and we'll call these our q-values. So again, we want the positive and the negative version. But our leading coefficient in this problem is the value 1, and the only number that divides evenly into 1 is 1. So then what we would do is we would take all our p's and divide them by all our q's. So in this case, if we do that, again, we'll get positive and negative, and that'll always be the case. If you took all of your p's and put them over all of your q's, well, you only have one q. So it's just take 1 and put it over 1, 2 and put it over 1, 4 and put it over 1, and 8 and put it over 1. So I put each of my p's over my q of 1. And so if we simplify that down, we can see that that's just those whole numbers, or those integers, I guess, since we're dealing with pluses and minuses. The positives and negatives, 1, 2, 4, and 8. So these are our 8 possible rational zeros. So in step 2 of finding the real zeros of a polynomial function, we're going to find the possible number of positive zeros and also the possible number of negative zeros. And we use Descartes' rule of signs in order to do this. And so to walk us through Descartes' rule of signs, we're going to start off with the case where we're trying to determine the possible number of positive zeros. So if we're trying to determine the possible number of positive zeros, we're going to look at our original function f of x. So f of x, what we're going to focus on is its signs. So starting from highest power to lowest power, so in descending order, what are the signs of the coefficients? So for the x to the 5th term, the sign is positive. X to the 4th term, the sign is positive. The x to the 3rd term, the sign is negative. The x to the 2nd term, the sign is negative. The x term, the sign is positive. And the constant term, the sign is positive. And then what we want to count is how many times we switch signs. So we call that the number of variations of signs. So from positive, positive, that's not a switch. But from positive to negative, that is a change of signs. Negative to negative, no. But negative to positive is a change of signs. Positive to positive, no. And so what we can see here is we have 2 variations of signs. And so what that means is the possible number of positive zeros could be that count that we came up with, which is 2. Or what we would do, that's not the only option, is we'd have to continue to subtract off 2 to determine the other options. So if I subtract off 2 from 2, that would bring me down to 0. And what that would mean is we're saying that there are possibly 0 positive zeros. Now you can't have less than 0, so there's no reason to keep subtracting off 2. And so these are your only options. So the possible number of positive zeros we have are 2 or 0. So it's one or the other. If we want to determine the possible number of negative zeros, we take our function f of x and we evaluate it not at x but at negative x. So that's the difference. So imagine if you took your function and everywhere there was an x, you put in negative x. Okay, so I'm going to go ahead and write that, so it's going to take me a second. But basically, again, all I'm doing is taking my function and evaluating it at negative x. So now you do need to be very careful here with the powers, especially in regards to signs, especially since everything is based off of the fact of what kind of signs you have. So it is easy to make a sign mistake, but you want to be careful. And so remember, if you take a negative and you raise it to an odd power, it's going to come out and still be negative. If you take a negative and raise it to an even power like 4, it's going to come out to be positive. And so a positive times a positive is positive. Take a negative and raise it to the third power, it's going to come out negative times this negative 6. Well, negative times a negative is a positive. Negative to the second power is going to come out positive, but then positive times a negative 6 is negative. A negative times a positive is negative. And then we have the positive 8 there at the end, and that's not going to change because there's no x value. So then at the end of the day, the number of variations of signs, we're going to still count those. So from here, negative to positive is a change of signs. Positive to positive, no. Positive to negative, yes. Negative to negative, no. Negative to positive, yes. So in other words, do I switch signs? And you can see that there's a count of 3. So what this means is there's possibly 3 negative zeros, or you have to keep subtracting off 2. So if I subtract off 2 from 3, that brings me down to 1. There could be 1 negative zero. And then I'd go to subtract off 2 again, but then that brings me down to a negative value, and you can't have a negative number of zeros, so there's no use talking about that. So my possible number of negative zeros at the end of the day are 3 or 1. We're going to go ahead and continue with step 3, which is determining the upper bound and lower bounds of our function f of x. And we're going to use synthetic division testing to do this. And an upper bound is basically the highest value a zero can be, meaning there are no zeros higher. So once you determine what the upper bound is, you can stop doing your synthetic division testing because you know there are no zeros higher. And the same would be true for a lower bound. So you would do your lower bound testing, and once you determine a lower bound, you can stop doing your testing because there will be no zeros lower. Now, when you do your upper bound testing, you're going to do it on the positive values of the possible rational zeros that you determine in step 1. So our upper bound testing would be on 1, 2, 4, and 8. And you would actually work in that order from smallest to largest. So that way it could be limiting. So I would start with the value of 1, and then I would list the coefficients of my function, which are 1, 1, negative 6, negative 6, 8, and 8. And then I would go through my process of synthetic division, pull down my first value, multiply it by my a, combine, 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 and multiply it by my a, and combine. And so again, a here is the value of 1, which is boxed off over here. So that's how I was doing that. And then the way you would determine if you have an upper bound from your synthetic division is you would look at your resulting row, and if all the values are positive or 0, you know you have an upper bound. So we can see that is not the case, so 1 is not an upper bound. And so if it's not an upper bound, then you need to move on as far as your upper bound testing is concerned, and you would move on to the value of 2. Also notice the remainder here is 6, it's not 0. So that means that 1 is also not a 0, because the only way it's a 0 is if that remainder is 0. So we can see that 1 is not an upper bound and it's not a 0. So we'll go ahead and move on to the value of 2 to test. We're going to go ahead and continue our synthetic division testing with the value of 2, since that's our next step. And our coefficients are still 1, 1, -6, -6, 8, and 8. So again, we pull down that leading coefficient, multiply by our a, which is 2, combine, multiply by 2, combine, multiply by 2, combine, multiply by 2, combine, and then multiply by 2, and we combine. And we can see that 2 is not an upper bound because our last row here is not all positives and zeros. However, we can see that the remainder is 0, so that tells us that the value 2 is a 0, because remember, if you do your division and your remainder ends up being 0, then that means your a value is the 0. So 2 is a 0, which also means that x minus 2 is a factor. So always x minus your a value is a factor. So or x minus your 0 is a factor. So part of the factorization of our original function is x minus 2. Now we don't know the rest of it other than when we divide off x minus 2 from our original function, we get this depressed equation here, which is all these coefficients in our last row, excluding this remainder piece. And so 1x to the fourth plus 3x to the third plus 0x squared minus 6x minus 4 is our depressed equation. So it's always 1 degree less than what you were starting with. So we were degree 5, so we're now down to degree 4, and we use these coefficients 1, 3, 0, -6, -4 to write our equation. So then now, when we continue on with our synthetic division, we're going to be doing it on that depressed equation. So the coefficients we use are no longer going to be our f of x coefficients. They're going to be 1, 3, 0, -6, and -4. And actually, because 2 was a 0, we need to repeat test with that 2 because it could be a repeated 0. We don't know. So we have to continue on with the test. And so now we're going to go ahead and perform that synthetic one more time. And we'll multiply by our 2, combine, multiply by our 2, combine, multiply by our 2, combine, multiply by our 2, combine. And this time around, we see that that resulting row is all positives. So 2 actually is an upper bound. So that means we don't need to test any values higher than it because we know we're not going to have any zeros higher than the value of 2. So I don't have to test 4 and 8. So 2 is an upper bound. 2 is not a repeat 0, and we can see that because the remainder is not 0. So it's not a repeat 0. And so that's what these synthetic divisions tell us. Now, we can see that at this point we've only determined that there's one positive 0. And we determined that 2 works, and it didn't repeat, so it occurred once. But remember, from the possible number of positive zeros test, it said that we could have 2 or 0 positive zeros. Well, we only have 1 at this point. That means there has to be one more. So that's probably going to come later on in the problem. The thing is, it'll just end up being a positive 0 that isn't rational. So it's going to be irrational. So we'll see that later. So then now, at this point, since we've determined the upper bound, we don't need to continue with the positives anymore, and we're going to move on with the negative values of the possible rational zeros, and we're going to do lower bound testing. So I'm going to go ahead and erase my little x's here because we're going to now focus on the negative values. And again, we'll still work in that same order. So we'll start off with synthetic division on -1 and then work our way down to like -8. So we're actually starting with the larger value of the negatives if you think about it. So when we use our coefficients, we're going to continue to use from our depressed equation. So 1, 3, 0, -6, and -4. So perform the synthetic division, pull down that leading coefficient and multiply by the -1, combine, multiply by -1, combine, multiply by -1, combine, multiply by -1, and combine. And see how that remainder is 0? Well, if that's the case, then we know that -1 itself is a 0. Now, as far as whether and then if -1 is a 0, that means x minus a -1, which is x plus 1, we know that is a factor. And so we just divided out the factor x plus 1 from our depressed equation, x to the 4th, dot, dot, dot. So then now we have a new depressed equation with 1 degree less than that 4, so it's now degree 3. And it's going to have the coefficients x to the 3rd plus 2x squared minus 2x minus 4. So we've factored that factor down. And then as far as determining whether -1 is a lower bound, we again look at that resulting row. And what we're looking for this time is whether the signs alternate. So positive, negative, or negative, positive. If they do that all the way across, then you would say that -1 is a lower bound. And then as far as zeros go, zeros can take on either sign, so whatever works for the problem. And so we can see that we are not alternating signs, so -1 is not a lower bound. But it was a 0, so since it's a 0, we now have to repeat our synthetic division testing just to see if it's a repeat 0, and we do it on the depressed equation, which again comes from that last row, and it has coefficients 1, 2, -2, -4. Don't include the remainder piece. And we'll pull down that leading coefficient and we'll multiply by our a of -1, combine, multiply by -1, combine, multiply by -1, combine. And we can see that -1 is not a repeat 0 because we have a remainder of something other than 1. And we can also see that 1 is not a lower bound because we're not alternating in signs. So what that means is we need to continue on with our testing. So we're going to go ahead and continue on with our lower bound testing, and we're going to begin with the value of -2. And we're going to continue to use our depressed equation with coefficients 1, 2, -2, -4. So we pull down that leading 1, multiply by our a, which is -2, combine, multiply by a, combine, multiply by a, combine. And we can see, because that remainder is 0, that -2 is a 0. And remember what that means. If -2 is a 0, then that means you have a factor. You have the factor x minus that value. So x minus a -2 is x plus 2. So x plus 2 is a factor of our polynomial. And so again, let's go ahead and break up our polynomial because we said we were doing division on this x to the 3rd piece. So we're saying when we divide by x plus 2, we get the depressed equation with leading coefficients 1, 0, and -2. and it's going to be 1 degree less than our polynomial here, which was degree 3. So 1 degree less is going to be degree 2. So it's going to be 1x squared plus 0x, which you don't really need to write, but I'll write it, minus 2. And so we can see now that we've pulled ourselves all the way down to a quadratic, so degree 2. So then what we can do at this point is we can actually stop with our synthetic testing, because there's really no reason to keep going, because once you're down to a quadratic, you can use the quadratic formula or factoring, so whichever works. So in this case, we'll use the quadratic formula to determine our remaining zeros. So if we use our quadratic formula, it says we take the, in our quadratic, I'm just going to list it here just to remind us what we're doing the quadratic formula on. Notice that your a value is 1, your b value is 0, and your c value is negative 2. And then the quadratic formula says you take the opposite of b, so that would just still be 0. Negative 0 is still 0, plus or minus the square root of b squared, which is 0 squared, minus 4 times your a, which is 1, times your c, which is negative 2, all over 2 times a. In this case, your a is 1. So simplify, you get plus or minus the square root of 0 plus 8 all over 2. But that's just plus or minus the square root of 8, which we could break down into the square root of 4 times the square root of 2. And the reason being is 4 is a perfect square factor that can factor out the all over 2. But then the square root of 4 is the whole number 2. So plus or minus 2 square root of 2 all over 2. But then 2 divided by 2, those are going to cancel out and leave you plus or minus the square root of 2. So that's our remaining zeros, positive and negative square root of 2. So we can see after all of that work that the zeros that we found through our synthetic division and our quadratic formula are 2, negative 1, negative 2, square root of 2, and negative square root of 2. And then the factorization of f of x is just x minus each of those zeros. So x minus 2 times x minus a negative 1, which is x plus 1, times x minus a negative 2, which is x plus 2, times x minus square root of 2, times x minus a negative square root of 2, which is x plus square root of 2. And so that is the factorization of f of x. So if you're asked for the zeros or the factorization, notice the difference between the two. And so we have completed the problem. Notice that steps 3 and 4 kind of work simultaneously together with each other. So just take a look back and maybe just read over the process and try to repeat it yourself.